we don't know how our solar system came to be, so we have to look at the other solar systems, and we do that. We have like the ALMA telescope. ALMA is a millimeter wavelength telescope. It's really cool. I can only encourage you guys, go on the website von ALMA. Wait, let me write it here. So this is like ALMA. Yeah, it's a millimeter wavelength. And it's basically observing solar systems that are in the process of being made. And what you see here is the red one is the dust content, and the blue one is the gas content. Yeah. So we have to rely on that, what we see there, to basically conclude how maybe our solar system came to be. And so what we thought that it's going to be way longer, but actually we find systems that are like maybe 1 million years old only. Yeah, 1 million years. And so that means maybe it takes like not as long as to produce these systems. This is no Man's Sky. No, this is no Man's Sky. Yeah. So basically what is happening here, just roughly, is we have gas and dust in a circular plane, and then we get like dust grains gonna clump together from rocks, from asteroids, from little planetesimal bodies, and at one point then we finally have a planet structure, right? So then we know already that the solar luminosity is eventually increasing, right? We learned that right at the beginning of I think the second science stream. We learned that. Okay, can we find this here? Wait, how is this working? No, where are the objects? Ah, there we are. Okay. Alright. Why is this not... Why is this not white? Ah, okay. Now we had to make it white, okay. So we learned that like in the second stream, we learned that the solar luminosity will eventually increase over its life. And if you're lucky, in 3 billion years, they can form a nini. Very funny. Again, hello everyone who just joined in. We are still at the beginning. You missed absolutely nothing. So solar luminosity, we're gonna measure it like in this case. So it's basically the luminosity we have, and this is the luminosity divided by the luminosity we have today. Yeah. So L is luminosity. If you have the symbol that uses with like a circle with a point in the middle, it means basically our sun. It always refers to our sun. I hope we're gonna gain some level of smartness. You will, I'm sure of this. So yeah, if you divide the luminosity of the sun by the value of today, this is the scale we have here. So we started out by 0, right? Then we make this 2, and this is like by billion years, okay? This is billion years. Then we have, like, say we have 4, 6, 8, and there we have 10. And this is like in billion years. Over the A? What do you mean? And this luminosity is like slightly increasing. Like this is nowadays, right? So this is like, let's make a... Yeah. So we are... Oh, great. We are at a point today, roughly like 4.5 giga years, yeah, is our age. And so solar luminosity is slowly increasing over time. We know that already. So sun is burning hydrogen. It's very happy with it. but some of it gets made to helium, and then then it's getting hotter and hotter. So it used to be like 70, only like 70% as much as luminous as it is today. So eventually the sun will leave the main sequence. The main sequence is as long as the star is burning hydrogen, right? After that, I think some of you know, it will become a red giant. It will not become a supernova, but it is expected that the luminosity will increase way beyond our like supportable life, like what we need to support life before the sun is even reaching the red giant phase. Okay, so we know also that the habitable zone, we learned that as well, the habitable zone does not solely rely on the definition of does the sun provide the liquid water? Like, is the sun hot enough to provide liquid water, or is it too hot to provide liquid water, right? We have another factor that plays into this. Because, and this is the atmosphere of a planet, not our Earth, not just the Earth, every planet, right? So we have the liquid water zone, but we know per evidence already that can we like change this here to that we used to have, like, the sun used to be under the freezing point of water, like and we still had liquid water on our Earth, yeah. So we know, so sun used to be not hot enough to support liquid water, right? Or that the luminosity, like, there used to be not enough luminosity to support liquid water on Earth. So luminosity used to be below freezing point, yeah. Was not enough for liquid water. But we still had it. Still, there is evidence that we had liquid water. CO2, yeah, most likely CO2. We don't really know, of course, but it is. We think that the CO2 content was way higher. Like, if you look at the rock structures, it supports that there used to be way more CO2 in the atmosphere. So, just joining the stream. Looking forward to learning some astrobio. Have a good stream. Thank you very much. That means if you have the sun here, so sun, and we have the habitable zone here, I think I'm gonna just use the circle. I'm making terrible. Let's just go to the next slide. I feel like I don't actually have enough room anymore. So we have our sun here. Great sun, lovely, always perfect sun. I'm gonna use the circles here. There you go. So if you do the range of the habitable zone, right? So if you have, like, okay, we say we have the Earth is here, whatever. Then the outer edge of the habitable zone is not solely defined by the luminosity of the sun. It's more like defined on the strongest greenhouse effect on the planet, right? So actually I'm gonna say what it is, like outer edge of the habitable zone. which I just shortened to HC, looks like a cinnamon bun, is defined by the strongest greenhouse effect, yeah? So basically, if it's getting like not cold, like the sun luminosity is not strong enough to reach there to maintain liquid water. If we have a strong greenhouse effect, we can still have liquid water. So basically, that's probably what was the case, right? So the luminosity wasn't strong enough, but we had a strong greenhouse effect and could maintain the liquid water. And the inner edge, like the inner edge, is defined by the weak greenhouse effect, right? So yeah, all right. The luminosity is like reaching the point of the edge, and we have liquid water. But if we also have a very strong greenhouse effect, then we might start getting a runaway effect where basically water cannot maintain a liquid state, right? That's why the habitable zones of any exoplanet needs to always consider not only the star, but also its climate, its biosphere, like everything, right? If we have if it's getting too hot and we get water vapor, yeah. So luminosity increases. However, an atmo can recycle whatever amount of sunlight it gets, so I guess the Goldilocks zone depends on the planets. Exactly. Absolutely. As much as the sun. Yeah, absolutely. That's the thing. The classic definition of the habitable zone is basically pretty useless unless we make a rough estimation. Like, we can make a rough estimation. There are still zones where any kind of greenhouse effect will not work, right? Or will have started a cycle that where you cannot recover. So you can still look for ranges that are valid. So in general, we have an increase in the luminosity, which increases the water vapor and atmosphere, yeah. Increase the water vapor in atmosphere. Or gravitational stretching from a gas giant or moon orbit. That can also allow liquid water, even without much greenhouse. Interesting. So if you have the water vapor in the atmosphere, of course, is also like a greenhouse gas, right? It also acts as a greenhouse gas. So it's increasing again the heat, like, right? Increasing again the temperature. I just shortened temperature to T.
Yeah.
Eventually, like, it will dissolve, like the UV light will dissolve the water in the atmosphere. It will reach the higher levels, will dissolve in like OH, and then like the hydrogen will eventually, like the atomic hydrogen will escape the atmosphere. And then we're gonna lose all the water, right? So UV light is it dissociate, right? The water. And atomic hydrogen will escape atmosphere, right? So that's the fate. That's the fate if it's starting getting too hot, and that's basically one of the loops that can happen. But we do not only have like water to consider, we also have to consider the CO2. And CO2 is very, very important, and that is one of the solutions for the faint sun paradox, which used to be not hot enough to maintain liquid water, but we still had it, right? So CO2 is a greenhouse gas, and it decreased gradually. It must have decreased gradually, because if it's decreasing, our surface temperature of the planet is cooling down. And that is the effect we looked in very detailed the last 2 times, called weathering, right? So we have an effect that is called weathering. Removes CO2 from the atmosphere. How that works, we looked at it. So basically, CO2 is combining with the water in the atmosphere. They are like forming some acid droplets. They fall down on like silicate stone. There's a weathering process that is taking place. It's gonna get washed in the sea and basically used there by the sea creatures, forming cells and stuff like this. And in the end, the carbon is getting stored in the ground of the ocean, right? Eventually, it will come back through like volcanism in mid-ocean ridges or something like this. But mainly, if you have weathering, that means if you have a lot of rain, that increases, and we will have more rain when the luminosity increases, because it means more water vapor. So we have more rain, we have an increased weathering effect. That means we remove more and more CO2 from the atmosphere and store it in our planet. Hence, temperature will go down. T decreases. Okay. So that's why if we look again at the boundary, we would think like what we usually think. We would think, okay, there's the sun, right? So let's say there's Earth, there's Mars, and there's Venus. What I'm now wondering is the zone conditions that are affected by the biology of the planet. Take Earth's oxidation, even for example, that was algae, right? Which had huge climate impact, state of water included. Yeah, everything has a huge climate impact, but the question is, how big is the climate impact? Like, we are looking here in the big picture, right? So we are not looking at the exact how we stabilize the climate today. We know like weathering is a stabilization factor, but we're not going to look at how exactly it's going to stabilize, right? With all the small details there is. Eventually we're going to end up on the rare earth hypothesis. So we're just going to go like in an overall broad view on that. That is like everything is in fact, basically, right? And that finding that out is very difficult. Like the simulations to find out every single detail. That's why in general climate modeling is so fucking complicated and takes so long. So anyway, the habitable zone used to be beyond Mars, right? And like below Earth. And we are talking about a habitable zone for an Earth-like planet. So you would think that when the solar luminosity increases, it moves outwards, right? It moves outwards in both directions. But what actually happens because of the carbon dioxide storage, because of the weathering process, is that it's getting narrower and narrower. So now, like this is the habitable zone. You saw the outer edge went inwards instead of outwards, and in the future, the habitable zone will be like there. Like beyond Earth, yeah, it will reach the 1 AU boundary, 1 astronomical unit. That's how far Earth is away from the sun. And that's not boobies. What the fuck? Oh my goodness. Okay. Okay, so we have here Venus. We have Mars. We have Earth. Okay, guys. Okay, guys. So, the habitable zone gets narrow, and the outer edge does not move outwards, right? Can't unsee it now, thanks shit, goddammit. Okay, so this is the future habitable zone here, right? And why is that? Why is that? It's because the carbon gets stored and we need the CO2 to sustain bioproductivity. And that's the crazy thing, right? That's the crazy thing. What we learned last time, actually, yeah, that eventually we won't have enough CO2 anymore to support life. But right now we are fucking up our climate so bad. Yeah, it's crazy to think about it. It's actually crazy to think about it. So we need a minimum amount of CO2 to basically support bioproductivity. It's not boobies. God damn it, guys. You're terrible. You're terrible. Okay, so having settled that, we now know about like the solar luminosity and the CO2, right? How we need that for life. This is why I failed in high school. This is why you failed in high school. 100% this is why you failed in high school. So now we're gonna come to the Cambrian explosion. So how did life come to be? Like, how did intelligent life come to be, right? And this is done to something called the Cambrian explosion. Cambrian explosion. Whee! How big is the habitable zone, and does the size change by the star? Yes, the star changes by size. The habitable zone changes depending on the star, of course, because you have a basic habitable zone supported by a star, right? So as I said, the habitable zone at the moment, at today's, like this is today's habitable zone. Can we find another color? I don't know, there. This. So this is basically, it's still before Earth and after Earth, right? But Mars is not included anymore. It used to be beyond Mars. Mars used to be in the habitable zone. It's not anymore. So, and this is the future habitable zone here. This is what it's going to be. But of course, if you have like a hotter star, the habitable zone moves by default more out, right? And you have a colder star, it moves more inwards. But as I just said, it doesn't really matter. It mostly depends on the biosphere of the planet. I mean, we have several cases where something is habitable that is not actually in the classical definition of the habitable zone. So the Cambrian explosions. What's the Cambrian explosion? The Cambrian explosion is often referred to as the Big Bang of biology, right? Big word. And what happened was there was a sudden increase in biodiversity in our Earth, yeah? Earth history. In biodiversity. It happened like, when was it? 500 million years? So it's nothing, all right? It's basically nothing. 500 million years ago, or 542 million years ago, something like this. If you look at the overall history, it's absolutely nothing. Years ago, and it lasted roughly 14 million years. This is of course all up to debate, right? Nothing there is sure, but we have here, this is billion years, right? This is how long we exist. 500 million years, it's absolutely nothing. It's like really recent in Earth's history. How long? Yeah, we are coming to this. We are coming to this. we are absolutely slowly coming to this. So I think we just, maybe I just gonna make that. Do we have like a one line? Okay, yeah. There you go. So we have here time. And we set here 0. Make here 2. No, actually make it look like this. 2, 4, 6, 8, 10 in giga years. By your calculations, about 3 weeks. Then like this is today 4.5. Actually 4.5 is not 5, so it's a bit before, right? Today. There. So the Cambrian explosion happened somewhere around 4 gigayears. After 4 gigayears. Okami, I don't understand anything what you write. I don't understand anything. So far I extended my take on Goldilocks just 1 distance and strength to sun, phase of water to 2 atmo cos. What? Okay, whatever, move on. So that means in here was the Cambrian explosion, right? Which is really a very, very short time frame, like a very, very short time frame in the history. So before the Cambrian explosion, we still had life, right? We still had life before, but before we had mostly microbiotic life and vegetation, right? Actually, no. We're gonna go more. Actually, yeah, no, we say it like now, before. Yeah. We, like, it's the first science stream, Okami. You can see my first science stream. I uploaded it on YouTube. That's where that's why we talked about all of that. Okay, so life before used to be is it microbiotic? I don't know. Something like this. Microscopic? I don't know. Microscopic and vegetation. Alga, I guess, and something like this, yeah. We can divide life into like 2 of the main groups. Life? No, not 5. Life. Now come the big words. It's just big words. It doesn't really matter, guys. We will get through it. We will get through it, okay? And this is a basically cellular organism. Two of the main groups and what they are like cellular organism. All right, Is it cellular? Cellular organism. Okay. So first one is prokaryotic. Cellular is correct. Okay. And the other one is eukaryotic. So prokaryotic is mostly single cell based organism. All right. Single-celled organism. Sounds like a music instrument, yeah. Like bacteria. They are very small. They have no nucleus, right? Okay, so very small. No nucleus. Or any internal structure, actually, yeah. Hey, Cozy. And the eukaryotes are single and multicelled. Membrane bound versus unbound. Yeah, see, I don't think that we have to know all this. I think the most important thing is like the single-celled and multi-celled. But of course, you can like, if you like someone who knows biology, it would probably be better to do this topic actually. But I don't know anything about biology. So I have to go with this. So that's mostly fungi or I don't know, plants, right? Plants. We are doing the science about biosphere lifespan. we are already here. We talked a bit. Actually, how do we have already so many slides? We just started. Didn't we just start out, guys? Holy fuck. Yeah, you're getting smart. So larger complex structures. With the eukaryotes. And the cells have a nucleus, right? The cells have a nucleus, yeah. Cells have a nucleus. So this is biology, right? I don't know shit about biology, so just let you know. So I just write this down. I write it down, and now you know. So from the Cambrian explosion, so everything branched out from there, right? So what we have is the first appearance of skeletonized, and that's important, animals, and they have a special name, even though we just can call them animals. So skeletonized. Z. Okay, and the word is metazoans. Right. Metazoans, guys. I think I'm correct, yeah. So these are just animals. And they're basically getting produced from the eukaryotes, from the eukaryotic cells, right? They're starting to make multi-cells, they're starting to produce like tissue, organs, yeah. So the eukaryotic stuff the multi-cells starting to produce nerve system and all this kind of stuff. So that is the birth of complex life, right? This is basically the birth of complex life. So eukaryotes organize to tissue, organs, nerves, whatever. So we have the start of complex life. Hey, Sven. We have, I don't know, have you been in a museum? I have been in a museum of that. I'm gonna steal some pictures. I stole some pictures. Don't copyright strike me, guys. So you can see this. If you go in a museum, we have so much evidence of this shit. There's so much everywhere in the world. Like seriously, the world is full of this. Our world is full of this. So I just show you some example how this looks like. So there's one of Canada, 508 million years old, detected in 1909. Super old, yeah. A Mera fossil. Whatever that means. There's one of Greenland, detected in 1984, 515 million years old. And there's like a newer one from China that just recently got discovered. Astronautes, thank you very much. A facehugger? Yeah, it's a facehugger. No, this is a facehugger. Okay, so we had the Cambrian explosion, basically sudden increase in biodiversity. Before, there was not much life. We had like this prokaryotes and eukaryotes, like, I don't know, living their life, just chilling, hanging there, doing whatever for years, for billion years, right? And suddenly, bam, alright, well, we don't want to just stay like that anymore. We want to become the cool guys. Yeah, learning stream. And so they were like, all right, we're gonna evolve now. Yeah, we're gonna evolve now. And they're to date, they're branched out, right? So they're branched out to different kinds of stuff. And like today, we can still find some of these. Some of these are actually still like findable, or like we are descendants from them, right? I think that self-assembly proteins is the coolest chemistry trick. I don't know shit about chemistry. I just know shit about physics. So yeah, so it branched out from there, and here we are. So we have to ask ourselves, how did it happen? And I don't know. Let's take this. Wait, what? Okay. And just make a little picture here, so people don't get bored. People like pictures. Those are your grandfathers, guys. Say hello to your grandfather. That's how they looked like. Can we like oh, I was holding the pen the wrong way. Okay, so how did it happen? There are some hypotheses. You're just here for the pictures? Yeah, I knew it. Yeah, so there are hypotheses. So, and there are, like, geology, like, I don't know. In university, once I looked out the window during a lecture, and there was a giant stone, and there were like 10 people standing around this giant stone, and they had like a paper, a block, and a pen, and they were just looking at the stone and they're writing down stuff. And I'm like, what the fuck they're doing there? And I was like, yeah, these are the geologists. These are the geologists. They're super into stones. They're very useful. They're the ones that find us. They're the ones that find the evidence about our history of Earth, right? So actually being a geologist is pretty cool. And so they found some evidence of what could have this caused, but we don't actually know. It's all like hypotheses. Would be cool to see. Yeah, I wanted to see the notes about this one stone. I think it was like a practice stone. Yeah, I guess every university has a practice stone for a geologist where they can write down stuff about the stone. Okay, so one is breakup of a supercontinent. Actually, I leave some space. Supercontinent. It even has a name. It even has a name. Rodinua. The later astronauts landing on the moon were geologists. It makes so much sense. Rodinua. I think, yeah, that's the name. I don't know why they gave it a name, but I gave it a name. Atlantis? No, not Atlantis. It's great, sad, it doesn't move much. Yeah, so, and another one is Snowball Earth. Yeah, it's called Snowball Earth, or glass, yeah, let's call it Snowball Earth. Why could this both, why would they say, okay, well, this could cause the Cambrian explosion? Rodinua? No, Rodinua. Yes, I don't know, yeah. Just call it supercontinent. I don't know why they give it a name, but I guess if you go really into detail into the stuff, everything has a name. Yeah, I think like there's so many, like it's crazy. You can really deep dive. That's what Okami I think gonna do. Okami wants to really deep dive in that topic. I can feel it already. Okay, so, and they say it could be caused by these events because they're, what they do is a separation. Yeah, they're separate. It's a genetic isolation. A genetic isolation can basically cause, because they give room, like if you remove a factor, like if you remove humans from Earth, then you would say, all right, like the animal, they will probably better out. Yeah, they will better up without us. So you know what I mean. So you remove one thing from the equation, and you leave more room for the rest of them. It's fine, Okami. Okay, so so they both basically lead to genetic isolation. Lead to. Wow, I can't even do arrows properly. Genetic isolation. Yeah, what's Snowball Earth? Don't worry, guys, we're coming to this. Snowball Earth means basically an Earth that is just covered in snow. I like that's the overall thing. So we have evidence that the Earth was completely covered in snow, multiple times. Are they called comet strikes? Yeah, later. And it was about like, they say it's about like 700, that's not a 7, to 600 years ago. Million. Million years ago. Million years ago, okay. Alright, guys, yeah, 700 years ago we only had snow. Yeah, we're gonna go with the comet's rays later on. So Cambrian explosions happened, what did we say? We said 542 million years ago. So we have evidence that before the Cambrian explosion we had the Earth completely covered in snow, which could have caused to genetic isolation and then therefore left room for development. Now the super breakup of the continent, like if you have a supercontinent and it breaks up, it's gonna change a ton. It's gonna change a ton. It's gonna change like the tectonic stuff, it's gonna change like the ocean flows, it's gonna change everything, right? So what we have here is like new ocean flows may have caused or like given rise to higher oxygen levels. And this is pretty self-explanatory. If you have suddenly more oxygen in the air, like, yeah, we're gonna have a better development of stuff, right? We also have like volcanism, right? Volcanism on the ground, contributing to the change of the chemistry of the ocean, right? So oceanic volcanism, changing ocean chemistry. Only if a fan of oxygen. Only if a fan of oxygen, of course. Yeah, of course. Like, of course, we all always only speak about life as we know it, right? We have to speak about life as we know it. Of course, there might be some creatures that maybe don't work with oxygen, but we don't know anything about them. You read that they have a much higher O2 content in the past? Oh yeah, right, that theory, right. That might have been even more in the past, and I don't know. No, later, I mean way later. Like at this time, the oxygen level was pretty low. I don't know. You might, like, when do the dinosaurs happening? They were also pretty recent. Like the dinosaurs got extinct 60 million years ago, right? So they must have, this kind of stuff must have even before the dinosaurs, but after the Cambrian explosions, yeah. Okay, another thing is called like sea level rise, and which allows shallow water, and you can imagine already that like if you suddenly have like shallow water, there's gonna be started biosphere stuff like this, or maybe have like an effect or something. But we can also just say that most likely multiple mechanisms were the reason for that, right? Yeah. Multiple mechanisms caused the Cambrian explosion. Okay, guys. We can talk a little bit about the mass extinction. I don't want to go too much into detail with this, but I guess we talk a little bit about this. So, mass extinction events can cause the same effect, right? And you don't have genetic isolation, or you do have genetic isolation, but simply by killing the other half of the population, right? That is something that could happen. So mass extinction events can also contribute to genetic isolation effect. We know we had like 60 million years ago, roughly, we had something called the KPG event. They gave it a name, and that was killed the dinosaurs. Plants were gigantic too. That's crazy. I don't whether gigantic spiders, I don't want to. What does it stand for? I have no idea. Let me see. Cretaceous Paleogene extinction event. Okay, I write that down. See, if it's going too many crazy names, I usually don't write it down for myself. But I just found the notes, and this is Cretaceous Paleogene extinction event. Yeah, it's a valid question. Sometimes I just think, okay, that is unimportant. I don't need to read this, but I give you the name so you can Google it. Usually, if I want to give you still the name, so and not just say, yeah, there was this event. So now you can just Google PKPG event, which is nice. Yeah, so we had like roughly like 3/4 of the population, whatever we had there, died. Like we know that like certain species survived, right? What survived, guys? Crocodiles, birds, mammals. Stuff survived. Not everything died. There's stuff that did survive. So and that caused a genetic isolation and could contribute it also, but this was way after the Cambrian explosions. Yeah, 3/4 died. Also crap. This is like 60 million years ago. The Cambrian explosion we just heard were like 500 million years ago. So yeah, that is not that is not really adding up. It's not really adding up. Anyway, this was not the only mass extinction event. Like, I think we are pretty clear by now that this event was caused by a giant impact from space. We have like evidence of a crater, which I think is in Mexico or somewhere there. The 60 Club crater, right? And yeah, I think this is massively known. What not is massively known is that we have other extinction events happening, yeah? So there were more mass extinction events. There was one mass extinction event where like 90% got killed, yeah? So what we have is basically frequent extinction events. Are happening. Yeah, it's actually happening. Yucatan area, yeah. Smaller ones, not as bigger ones, not as big as that. Like smaller ones. Okay, not these big ones. Smaller ones. what causes this? It's caused periodically. It's like they say every 100 million years, one of these events is probably happening. Yeah, so roughly every 100 million years. So that means if you take the dinosaur event into account, which was 60 million years ago, we're gonna have another one in 40 million years. Yeah. If you take, I don't know if we have to take this to account into the smaller ones, but we have records of mass extinction that's showing every 100 million years. Yeah. So I think we're fine for now. So how are they caused? We don't really know it. There are some hypotheses how these are caused. Like one is we got hit again 14 years ago or so. But was this a small extinction event? That's the thing. Like we're talking about the big enough to cause small mass extinctions, like 10K in diameter. Yeah, like 10K in the diameters at least. Yeah. Okay. So what could this cause? What could this periodically mass extinction events be caused by? They can be caused. One theory is that we are orbiting the solar system. Our solar system is orbiting a galactic plane, and we are going through a very dense area. Okay. So higher density area. This could be one cause, right? You know, we're like in a galaxy here. There's our galaxy. Our sun is like here. And we're like orbiting And maybe in this region, like there's a lot of going on in this region, and every time we orbit this region, we have disturbances, and the chance of something hitting us is high. We are orbiting, we are orbiting in our own galaxy. Every star also has like an orbit around the galactic core. Don't watch Seaspiracy. You saw? Alright, I don't care. Whatever, Romark. Just turn the galaxy upside down and it's the right way, okay? Just look from the other side. Then you're fine. Okay, another hypothesis is the presence of a ninth planet. Unusual clustering happening, like that alters the inclination, or like there's some slight evidence that this is gonna happen, right? And it's gonna alter like the comets, the route of comets and stuff like this. But that is like whatever. It's the same as like Nemesis. You know Nemesis? Who knows that? There's this theory that we have a companion star. You know? That we have a companion star far out. And that's gonna cause some trouble. Yeah, Sun's companion, exactly. The first one, oh actually this is 3, this is 2. This is enough to explain what we are experiencing, yeah? Like this is enough to explain this. Actually let's do it like this. So let's say yeah, we orbiting the plane should be enough. Yeah, the gravitational disturbances caused by the solar system going through a dense region in the galaxy. That is all we need. That is all we need. Yeah. Most likely not. But that's the thing in science, right? You cannot just ignore it. You cannot just not do it and say, all right, that's most likely not the case. You still have to say it. You still have to say that's a possibility, that it does exist, maybe does exist, that there's like slight evidence for it. You cannot just like throw it out of the window, right? You can't do that. So then there's a question of yeah, it's not close. Yeah, it should be very, very far away, like 1.5 light years, I think. Yeah, so super far out. Yeah. I wonder if the only life is DNA and all the rest is fruiting bodies. Okay, how much? Okay, I have some. Okay, so then is the question like, how big is what we hit? Like, yeah. So if you get hit by something that has a radius from like 100 meters, it's probably not do much, right? It has major local effects. It's gonna have major local effects. But like overall to our atmosphere, not much. Yeah. Very minor atmosphere effects. So if it's only like this size, that's probably not gonna help. That's probably not gonna help for like genetic isolation effect, right? Did they recently discover evidence against the ninth planet? Something to do with they now worked out the unexplained wobble of the sun? Right. Could be. But how did they explain the wobble of the sun? Like, is it really like, is it based? Is it just another hypothesis? Or is it completely based? So yeah, that's how it is. There's the evidence, 100%. Hey Orbiter. That is true, yeah. I mean, we are thinking that it's going to be a brown dwarf, right? I mean, that's what we think, that there is a brown dwarf that's orbiting it, and so still, if it would be closer, we would if it would be closer, we would notice the effects way stronger, right? It has to be way out because we are not noticing the effects that much. Exactly. What's about the gravitational effects? So if it would, the closer the star would be, the larger would be the gravitational effects. And because we don't actually notice them that much, that's why we think it must be far, far out. Yeah. You're stretching your memory here. Mercury has a large iron core, I think. Oh. Alright, I should read up on that. There's no gravity here, are you nuts? Yeah, the point is, they had, exactly, that's the point. Okami is getting it. That's we're getting it, yeah. So we have like, for 1 kilometer, we have like dust and atmosphere. Dust and atmosphere. Yeah. That would be dark, yeah. That would be very dark. Imagine we only exist because there's countless extinction events. I mean, we had this one event that like killed most of the marine creatures, like 90% of them, yeah. And yeah. So we probably also have like photosynthesis interruption. Could it be an epic war? Some aliens race that showed up everyone? Yeah, that could, yeah, it could, yeah. as always, it's the aliens. It's the aliens, guys. It is the aliens. Marine creatures. Yeah, imagine. But the mammoth survived. That's the most important thing. The mammoth survived, yeah. Now if we have like 10 kilometers, that's when everything burns. Burn it to the ground, yeah. Burn it. Wait. To the ground. That's where it happens, yeah. So atmosphere, ocean gets completely fucked up. That's where like we have starting to have really mass extinctions, and where we have maybe genetic isolation effect that is as large as the one from a breakup of a supercontinent or the snowball Earth, right? Would the dinosaurs not have gone extinct? Would we maybe have not existed? Could be. Could be. But that is not the case. Like, intelligent life, as we define it, happened already with the Cambrian explosion, right? So we are talking about intelligent life, and that does not mean us. I think humans maybe are pretty dumb, so we don't even cause where is it? We don't even count as intelligent lives, but anyhow, when we talk about the Cambrian explosions, it happened without it. It probably happened without the mass extinction events. But we could maybe think that we as human race would not have existed without dinosaurs dying. I called you all dumb, guys. I called you all dumb. Okay. Here we go. How long can Earth survive? Yeah, we all have our doubts. I think it's safe to say we all have our doubts with that, right? How long? Can we survive? Good question. Good question. We learned so far life depends on luminosity. I doubt the really dumb question would question its own intelligence. Yeah, of course. We're just memeing. The problem is what we're doing with our knowledge, right? They could not pay the high rent. Oh, they got evicted. Oh no, okay. So okay, life depends. Luminosity and CO2, right? That's what we learned. They had oil. Yeah, the dinosaurs had oil, so America invaded them. CO2 concentration. The CO2 concentration in the atmosphere, again, depends on the weathering rate. Yeah, we had that earlier, right? So for everyone who is new, who does not know what the weathering rate is, the weathering rate is a process caused by rain mingling with the CO2 in the atmosphere, dropping down to silicate stone, then causing a process where it's dissolved and then storing carbon in the ocean. So weathering is taking away CO2 out of the atmosphere, right? So that is what we know. We saw earlier that the luminosity is increasing over time. It's getting hotter and hotter. We also know that we were able to sustain life in liquid water even though it's getting hotter. So there must be have a correlation somehow, yeah. So if we go here, hello, do this again. So most likely the case was like this. The luminosity is increasing and the CO2 was decreasing, right? And CO2 decreased. This means that even though the luminosity of the sun was increasing, the temperature stayed in a level that was sustainable, that could sustain life, right? So we know that. But it's getting stored more and more. Yeah. So CO2 is meant to sustain our climate, but if the weathering gets increased more and more, like it's getting hotter, more vapor, water vapor in the atmosphere, more rain, more CO2 gets stored. So, and we saw earlier that the habitable zone will go narrow because of this. So eventually we will not be able to sustain habitable life simply because we're gonna run out of CO2. Alright? CO2 will sink more and more. And yeah, then we won't have enough to make photosynthesis. Yeah. So yeah, that is basically one fate. That is one fate we're gonna have. So the cycle is like this. There we have the sun. The sun is increasing mean global temperature. The CO2 in atmo is also increasing the mean global temperature. If it's getting hotter, we increase the loss to hydrogen into space. And if it's getting hotter, also we like actually why did I do that? Increase silicate rock weathering. Silicate rock weathering. We need like about 10 parts per minute to 100 like 10 parts per minute of CO2 is needed. Wow. For photosynthesis. Does weathering store CO2 quicker than seismic events like volcano eruption and like restore it to the atmosphere? Yeah, it's gonna get restored to the atmosphere. So we saw last time how like the circle works. How we have like, what is this? How mid-ocean ridges. Shit. Sorry. So we closed the global carbon cycle last time. So we saw how like mid-ocean ridges and like in general tectonic activity like returns the CO2 to the atmosphere, and it's like basically a cycle. And weathering, yeah, it can store CO2 very quick, and it absolutely depends on the weathering rate. So that means it's going to increase. It's going to increase over time. Also, it depends. The bioproductivity is a very important factor here, right? Bioproductivity enhances all of this, right? It enhances this as well. And it needs to be taken into account, definitely. So just to write this down again. Yeah, in the future we will be, yeah, exactly. We can take measurements, but I think instead of doing that, we should rather decrease the solar luminosity somehow with mirrors or something like this, yeah. I think before we come to this, we will probably be extinct already though, yeah. Most likely. So we have a feedback between the biosphere and CO2 storage. Yeah, by that time we will be cold. Yeah, so like the Earth cools down by enhancing silicate rock weathering, right? Enhancing so we're maintaining a level, and this is like I don't know, there's a thing called Gaia hypothesis. Do you know this? Probably you have. Like, it's kind of controversial. It basically means that the biological system is a self-regulating system that favors life, in a way. I hope that before that even becomes a problem, especially with our currently activity of pumping insane amounts of CO2 into the atmosphere anyway, we have become an interplanetary or interstellar species already. Yeah, I think we all hope that, yeah. It's regulating, yeah. It's maintaining. The evolution of the climate did affect how much CO2 is in the atmosphere. The CO2 concentration regulates the weathering, and there's another effect that we have to take into account: continental growth. Continental growth is also enhancing weathering. So that means if you have a lot of rain and you don't have earth, like you don't have the silicate rock, as Peck said, you have to find all the silicate rock. That's why like ocean planets have a longer lifespan, right? Ocean, like if you have an ocean planet, you have a longer lifespan of the biosphere, like, but with us, the continent grows more and more. We had more continental growth, so we could have more weathering, and that's gonna store more CO2. The Gaia thing before, meaning that the Earth is a whole, yeah, the Earth is a whole biological system, yeah. No, not Gaius, Gaia. Not Gaius, Gaia, yeah. Another thing is lowering of the mantle temperature. Like the Earth is cooling down, right? So the lower mantle temperature, less. Like if you have like a lower temperature in the mantle, Like we don't have all this volcanic activity. So we have a decrease in the spreading rate. We called the spreading rate last time, right? So we call it, yeah, decrease in spreading rate of CO2 from the ocean back to atmosphere. So that's also an effect, right? So we have less outgassing. We have basically less outgassing, yeah. So in the future, as more and more CO2 gets stored, yeah, it gets stored more and more. So in the future, the temperature does only increase via outside effects, aka the sun, right? Sun. Now that is very interesting, right? That is very interesting. We live in a time where we have global warming, where we talk about we have to decrease the CO2 from the atmosphere. We have too much bloody CO2. And here I am talking about how we're gonna die because we're gonna lose all our CO2. Isn't that fucked up, guys? Isn't that fucked up? I think this is very fucked up. But it is what it is. Yeah, eventually temperature will increase and we will overheat the biosphere. Okay. So eventually sun becomes so hot. Too hot. That will eventually happen. In the time frame, we are going to the time frame. We're coming to the time frame, guys. Don't you worry. I'm still waiting for you to explain that. What do you mean? The global warming? We all know. We fuck up. We pump it out. We pump the CO2 out. Like, instead of storing it. I mean, the storing process goes over a million of years, right? Like the reduction of the CO2 in our atmosphere. Does precision affect global weather? Right now, we should be warming, and precision has an effect. If precision has an effect, yeah, but most likely not in that range. Not in that range. Will we lose our ocean? Yeah, of course. We will eventually. Water will get dissolved. We could maybe, if we still store ocean in the crust, we could maintain it there. If it has no chance to leave, you know, or if it goes so cold that it freezes. But I don't know. Could be that it becomes cold instead. You know. No. That's the thing. So when I'm talking about the things, we're talking about a long time frame, alright? We're talking about a very long time frame. So if you have this today, hello? Yeah? So there's a CO2 level. There's the minimum. There's a time. Let's say here's today. This is today, guys. And so the CO2 used to be very high. Yeah, it used to be very high. And then it goes down. And it goes roughly to this level. There. And this is up to debate. This point, but we are talking about a time frame. Roughly around 600 million years. Like, and roughly, like, it could be, we could still increase it. We have to take into account, don't forget the bioproductivity. It depends all also on bioproductivity. So the models are different. Different kinds of model, say different kinds of data, but in the end it's gonna be like 600, 700 million, 800 million, but it's not gonna be much larger than that, alright? We need to breathe more, yeah. So now we're living, like now we're doing like something in a very, very short time frame, yeah? We increased our CO2 output in like 100 years, okay? We're not talking about this. Like when we're talking about CO2 is gonna go extinct and that therefore we are going to extinct, we're talking about this much of a time, right? It doesn't matter right now. Who cares right now? Yeah. It will, yeah, that's true, yeah. Before Squadron 42 gets finished. Absolutely right, absolutely right. So, there you go, guys. Finally a nice graphic. Now, when we call about life is getting distinct, what life? What life we are talking about? Prokaryotes, eukaryotes, complex life? Alright, so first off, they all have a different temperature range, right? Like the three principal life forms have a different temperature tolerance, right? Tolerance. So if you go like prokaryotes, wow, how about proper writing? Prokaryotes. It's have like to 2 and 100, like 2, 100, 130 degrees Celsius. The eukaryotes have like 5 to like 45, 60 degrees Celsius. In complex life has 0 to 30 roughly 45 degrees Celsius, yeah. We have to stop using Latin for science. I agree. I fucking agree. I so agree with you. I'm so done with this. So what we see here, but we had the prokaryotes, right? So we go back here, and this prokaryotes started out first, then the eukaryotes, then we had complex life. So if we go here, this is the surface temperature. This is the surface temperature of Earth, right? We started out here. 100 degrees, boiling water. So then it went down. Why did it go down? Yeah. How would you call these life forms? Little life forms? Very little life forms? Little life forms. Extreme little life forms. Okay, so what we had here, like this is happening together with an increase of continental area, yeah? Continental growth. I don't know. Yeah, can we like, does this work? Yeah, look there. Continental growth. So as the continent grows, we learned that if we have more continental area, we have an increased weathering rate. That means more CO2 gets stored in the ocean. And so the temperature went down. Yeah, the temperature went down. Is it the same for the Earth's core? I don't think so. It's not freezing, it's just cooling down. Roots of you run deep. They are green? Oh, damn it. How dare you lecture us here? How dare you lecture us? We are plebs. So you can see here they are like quietly divided on the when we had the sudden drops, when we had the sudden drop here. But this is today. This is 1 billion years, and now here. This is where it starts, right? This is where the Cambrian explosion comes into effect. Boom! Complex life. Look at this. Look at this. Look at this glorious increase of complex life right here. There. Isn't this glorious? Absolutely glorious. But the Earth's crust is a solid. Is it getting thicker as it cools down? I don't know. You have to ask the geologist. Don't ask me. Alright, so what we see here. Yeah, lower temperature is good for life. That's what we see here. Look, prokaryotes can exist with like 100 to 130. Yeah, Earth is cooling down. Yeah, that's the problem. We had that here. Because Earth cools down, the mantle temperature goes down. We have like a decrease in the spreading rate, so we are returning less CO2 into the atmosphere. So we see eukaryotes, they're good like until 44, some are at 60 degrees Celsius. So yeah, that you see when the temperature went in the 40 direction, like you can see that the eukaryotes started to like really come to life. It went even more down, and the generally cooling of Earth is also a reason why we just could have had this Cambrian explosion, right? That's fine, that's fine, that's why I'm telling it you again. So I'm telling it again. So and now what we can see here, that the ultimate lifespan of the biosphere depends when the prokaryotes die down, right? Who gives a shit about complex life? Who gives a shit about that, guys? We will die. Yeah, 0 is today. Exactly. 0 is today, guys. This is today. There. Today. Yeah, exactly. The complex life could vanish, but we would still have the eukaryotes, and at the end we still have the prokaryotes. And here, by the way, we have the atmospheric CO2, and we can see that's actually the increase, like it's pretty stable here, and it's you see how slowly it's going down in the end, right? So yeah, 1.5 giga years, guys. 1.5 giga years. That's when the prokaryotes die. We're gonna die way earlier. We're gonna die probably like 600, 700 million years. So out of all this life, yeah, out of all this lifespan, out of 6.2 giga years, we only have the very small time frame of complex life. That is it. That it is, guys. So we have like only a fraction of Earth's biosphere lifespan. Is habitable for complex life. What am I drawing? Yeah. because eventually there will be no CO2 left to even support them. If there's no CO2 left, then yeah, that's it. Yeah. Yeah, complex organisms are basically made of more complex eukaryotes, but still, it's gonna has a lower temperature range, right? That's the thing, guys. That's the thing. So, next science stream, guys, which I will hopefully do within the span of 1 month, we're gonna talk about the rare earth hypothesis. And that is very important. Yeah, this is still the one from today. This is still the one from today. Don't worry. So, and that what we learned today is very important for that, right? If we have a rare Earth, if Earth's planets are even rare, and we only have this narrow window for ourselves, for complex life that we can even detect alien species, right? That narrows it down again. Like that goes the chances way back of even finding. Yeah. So we finally made the circle, guys. We finally made the circle. We talked 3 streams now about the Earth system, and it's a rather complicated topic. I have to say, guys, it's a rather complicated topic. It's not my main field, so but it's super interesting. It's super interesting. Because the sun is still increasing, Rumhock. In the end of the day, the luminosity of the sun is still increasing. And if all the CO2 is stored, the sun is still increasing. It's still going up. Right? Yeah. Now, next stream we're gonna talk about the rare earth hypothesis. That is, yeah, basically how likely is it that we will find intelligent life out there? How are we gonna, if we're gonna find it? Yeah, how's the likelihood of us finding any kind of intelligent life out there? And we're gonna finish the whole topic of astrobiology with the Drake equation, I think. Yeah, we're gonna finish it with the Drake equation. But anyway, I just wanna make a little summary here, which I finally prepared for the first time. I realized I never make good summaries in the end. So I for the first time ever, I prepared a summary before the stream. Drake are shit. What is the likelihood of finding intelligent life, say, here on Earth? Good question. Good question. Okay, so we learned theory of Earth. Like this is what we learned over the whole streams, minus the first 2, which were a different topic. Sadly, the first, how we find exoplanets, is still lost. I'm thinking about making a video about it just for YouTube, just to round it up. I hate that it's lost. I hate it so much that I lost that stream. Like I seriously hate it. Okay, so we generally learned that the temperature of Earth is regulated by the global carbon cycle. The main negative feedback is provided by weathering and mediated by the biosphere. Negative feedback is meaning it takes CO2 away, right? We learned that the Earth's temperature went down in the past due to the continental growth and decline of the outgassing at the mid-ocean ridges, right? Continental growth affects the weathering, affects CO2. We learned that's because of this, the temperature in the future will rise only due to solar luminosity, right? The effect outside will be the final effect. We also learned that the Cambrian explosion was probably the cause for dramatic environmental changes that cooled down the Earth and therefore like increased biodiversity. That the biosphere is maintaining, the whole cycle is maintaining all of that. And we also learned that prokaryotes, eukaryotes, and complex life will be extinct in reverse order. And that the final lifespan depends only on the prokaryotes of the biosystem. That's fine, that's fine. No, we are all, guys, we are all intelligent somehow. Isn't that all just theoretical? Yes and no. There are different kinds of theories, like we learned for the how did the Cambrian explosion happen? That is theoretical or hypothesis, but we know it happened, right? We know it happened. There is no debate on that. We know it happened, and that's like a lot of things, right? Like the cause of the frequent extinction events, we know they happen, but we don't know really. It's still a debate on how it happened. There is no theory about that the luminosity of the sun is increasing. It's increasing. No, you don't have to go. Yeah, we go back in time by going and looking into the stone, right? We cut open the stone, we look into it, and we see the past. It's the same as we see the past when we look into in the sky. Like the light that is reaching us is from the past as well. And we can also look into the past of our Earth if we look into the stones. Yeah, we have a theory for gravity, which hopefully is correct, but we know it's a thing. Like, if I let this pen fall, it's falling down. There, it's there. It's and we can cut open the stone and we find these, right? We find it. It's there. It's not make up here. We find these. Earth is like a tree. Yeah, exactly. Like when you cut open a tree, you can count how old the tree is. And that's the same with Earth. I saw you push the pen down. That's so Mask, that's why I said at the very beginning of the stream, when I was talking about how do we find exoplanets. We talk always about life as we know it, and we should the Drake equation takes only effect life as we know it. It bothers me as well. It bothers me as well, but that's how it is. Like, if you think about different kind of lives, where would you even start? You would have to make them up from scratch, right? We can't even imagine that. So yes, all this stuff, all the things about astrobiology and how we find aliens we only talk about life as we know it. It's very important to remember. I'm just a hologram. That chair creates a type form of life. I'm using IO, and thank you for reminding me in this case that I still have to do that. There you go, guys. If you wanna... Hello? Oh. If you wanna read up, this is where I base my knowledge from. Yeah, these two books. There you go, guys. Go and read if you want to. It's very interesting stuff in them. And the program I'm using is Ink.io. Ink.io. There you go. There. All right. More power to holograms, yeah. Does our sun tool take to its neighbors, but at glitch! No glitch, you missed it! Thanks so much, Glitch though. Thanks so much. Oh my goodness, imagine subbing to me and cannot even watch my streams anymore. Yeah, we have to find other methods to communicate. If we find them, we have to find other methods. It's gonna be too slow, yeah. Not sponsored? No, this is just the books I read about it, guys, yeah. So I forgot it always to say at the end. So guys, that is the end. I think I'm gonna stop here now. I'm gonna say guys, thank you so much for being here. Seriously, I very fucking much appreciate it. Like, I rambled a bit today. I think last time was better. I'm a bit unsatisfied with myself today. I feel like I didn't talk properly today, but I think we understood the problem. We're visiting family? Alright. We're gonna upload it to YouTube, guys. If you wanna see it in double speed, I'm gonna upload it to YouTube. Anyway, next science stream, I don't know when it is. I will try to make it, depends on my lectures and stuff like this on university, but I will try to make it within a month. And the topic will be rare earth hypothesis. So that's gonna be great. I'm looking forward to that. I'm actually quite happy I'm done with the Earth system. I'm done with. I'm very, very happy I'm done with the Earth system. I'm like, this shit is so fucking complicated. We scratched the surface here. We scratched the surface. So if you're interested in that, go read up. Go read up on this. And again, the warning to the end. If you Google Cambrian explosion, be careful. Be careful. There are a lot of people that misusing it and trying to use it to prove points that are not very scientific. So anyway, guys, I hope you all have a great rest of the Sunday. Yeah, and enjoy your Sunday. And I will not be streaming on Monday because I'm gonna get my vaccine. I'm gonna get the Wi-Fi in my arm, guys, on Monday. So I will not be streaming then. So about the future reading, so we can prepare for our next talk. Yeah, prepare for our next talk. Rare Earth hypothesis. Yeah, I get my 5G upgrade on Monday, so I will be back with Star Citizen on Tuesday, guys. So yeah. No glitch. Oh, poor glitch. Alright, guys. See you later, guys. Live long and prosper, every one of you guys. Bye bye. No homework? Oh god, I have to prepare homework for the future, guys. I'm gonna have to prepare homework. 100%, I'm gonna do that. Peace.